Okay, this is 2.8 practice. I did already type this into Desmos, and I found this equation here, and it gave us a graph that looks something like this, and it told us to use the quadratic model to find the residual for this point for a diamond that had 3.61 carats. It costed this much money, which that's a lot of money for a diamond. Anyway, that's our actual price minus, and our predicted price. We have to take that 3.62 and plug it in here for those x's, and it gave you this amount of money. Okay, so our actual minus our predicted, our residual is a little bit over $14,000, which means when we drew this line here, that this point here, this 3.61, this diamond, we paid $14,000 more than what we were predicting. Or not, we didn't buy it, but the person who has enough money to do that. Okay, number 2. I'll put this into Desmos and show you. Okay, so this is our data for number 2. This is the speed, and the Y is the miles per gallon for vehicles at different speeds. So we're going to calculate the least squared regression line, and they want us to use a quadratic model. So if you remember, we type in y1 tilde ax1 squared plus bx1 plus c. And this gives you the a, the b, and the c. Here is that graph. There's that equation we came up with. Okay, our residual is the actual minus predicted. Okay, and with this one, we're trying to find the car traveling 60 miles an hour. So in our data, the car guy 60 miles per hour was 31.4. Okay, miles per gallon. Okay, so the actual, this is the actual that we have. 31.4. Our predicted, we have to take this 60 and plug it in right there. So negative 0.0083 times 60 squared plus 0.7396 times 60 plus 16.0303 gave us a predicted of 30.53. Okay. If I take and subtract those, I get a residual of 0.8737. Okay. Now, to interpret this, so at 60, we are that much over than what we predicted. Okay. The actual amount, actual miles per gallon, was off. Let's just not say off, let's say above what was predicted. Okay, so it's a good. So that's that one. Okay, so number 3, we're looking at North American population growth from 1700 to 2012. There's different dates here that we're going to use here, and x equals, it's the year since 1700. So 312 years after that would be 2012. Okay, so we're going to use this data. We're going to find the exponential model, draw a little scatter plot, and then find the residual for 2012. So I'm going to go to Desmos and do that. Okay, so here we have the data. X is the year since 1700. So in the year 1700, which is 0, there were 2 million people. 100 years later, in 1800, there were 7 million people in North America. You can see how we've really grown quite a bit. Okay, so yep, you can see that. It looks like a good exponential model. So we're asked to find the exponential model. So if we put that in here, we'll have y1 tilde a times b raised to the x1. Okay, so there's our model. We can see here at the bottom what our a and our b are.
So we can, part A, here's our equation. Part B, there's our scatter plot.
Okay, from Desmos, we have our equation, the A and the B. Kind of drew a little scatter there. And then part C says here to interpret the residual. Residual equals the actual minus predicted for 2012. So 2012 was this one right here, had a population of 351 million. So our actual was 351 million. Let's see how good our prediction was. So we got to put the 312. Okay, so 312 goes in here. So 5.543 times 1.013 raised to the 312. It gives us 311.8. Okay, so if I subtract those, I get a residual of 39.3. So it's a positive residual, which means when that line is drawn, okay, at 2012, that the point is above what we were predicting. Okay, so the actual was 39.3 million more than prediction. Okay, and number 4, a student takes M&Ms, dumps them out. The ones with an M written on that are facing up, he eats, and the other ones he puts back in. So the first time there were 30 M&Ms. He then dumped them out again, ate the ones with the M's on, and there were 13 left. And you can see it kept going down, okay, because there was more every time. So we're going to put this in Desmos, find the exponential model, draw a little scatter plot, and interpret the residual for the first course. So the first course was 130. We're going to interpret that residual.
Okay, so here's the course and how many M&Ms were left. Okay, so it tells us to do an exponential model. So we use y1 tilde a times b raised to the x1. As you can see our a and our b here. And if we hit this thing here, it gives us a little bit of a better model there, so we can see there. Kind of interesting. How many would you expect to be up? How many m's up? About half every time, right? And that's our model here as well. We have about 50% every time. That's why they have that 50% for that B. About half of them are going every single time. Okay, so there's our equation.
Okay, so from Desmos, we have our A and our B, our equation there. There's our sketch of our graph. Part C, we want the residual for the first one. Residual equals actual minus predicted. How many times are we going to write that? Okay, our actual for the first course was 30. Okay, we had 30. How many would we predict? Okay, so if I plug a 1 in up here, we have 58.55 times 0.505 raised to the 1. We would expect 29.57. Okay, if you take 30 minus that number, you get 0.443. So interpretation of that, the actual was 0.43 M&Ms above predicted. Number 5 has this problem, and it's the walking speed and the city size. So maybe the smaller city, the slower people walk. I don't know. That'd be kind of interesting to study. Anyway, so they want to know which of these two models is a better predictor. So is the quadratic model better or the exponential model better? Okay. Now remember, in a residual plot, we're looking for a good scattering across, okay? This one kind of sees a little bit of a pattern there, so that's not the best, but you see a good scattering across here. Exponential would be the better model. Okay, number 6, also looking at baseball salaries here. Average salary in the year, so you can see it kind of probably increasing, but anyway. So we want to know, is the quadratic model better or the exponential model? Okay, so this one, looking at the residual plot, you notice this one kind of follows a pattern here, doesn't it? Okay, this one would be a better model. It still has a little bit of a pattern, but it has a decent scattering. So quadratic would be a better model there. Okay, so number 7 here is looking at stock prices and what percent of change in the company there's been. So if we could predict one from one year to the next, that'd be great. You could make some money. But anyway, we want to interpret the slope. So we're going to write down the equation first. Okay. Okay, so here's our equation. This is our slope. Okay, so interpret this. Remember, slope is this over 1. So it's the change in the y. So the y was the change in 2013. And the x is the change in 2012. Okay, so we predict. So we would say for slope, for every 1% increase in 2012, okay, we predict a 0.396% increase in 2013. Okay, so that's part A, talking about slope. Part B, does the y-intercept have any context? Okay, our y-intercept would be where my x is 0. So if we think about x being 0 here, that definitely has some meaning here. So yes, it has meaning. It says that if there was 0% change in 2012, we predict, okay, you can go up here, actually from our equation, 24.9% change in 2013. Point C, okay, this is Boeing, okay, the airplane company, and they do other things too, but describe what that effect has on there, okay? So with that point there, notice it's kind of in the middle of our x's, right? So that point just kind of shifts it up, okay? Now if that point would be over here, then it would take it and shift it this way, okay, like this. But since it's right in the middle, it just increases the y, okay? So it increases the y-intercept, and it does not affect slope much. Okay.